Legacy enterprise defense architecture evaluates digital payloads at isolated checkpoints. A web application firewall, for instance, intercepts and parses inbound HTTP requests to determine if the specific content of that request is malicious. Endpoint security operates on the same isolated logic. An EDR agent monitors local host activity, scanning incoming binaries against known malware signatures to block execution or quarantine the process. These controls evaluate a payload strictly at the exact moment it crosses a sensor boundary. If the payload syntax appears legitimate in that fraction of a second, the localized control permits it to pass. Advanced persistent threats bypass this model by employing living off-the-land tradecraft. These are sustained, goal-directed campaigns that deliberately use legitimate capabilities to navigate an environment. State-sponsored actors acquire valid access, then maneuver using native administrative tools, approved remote services, and centralized deployment scripts. To an isolated sensor, this activity perfectly mimics authorized IT operations. Attackers obscure their actions further by hijacking valid session tokens and tunneling command and control instructions through approved encrypted channels, entirely blinding traditional deep packet inspection. When an attacker operates legitimate credentials through an encrypted tunnel, analyzing the isolated content of the local node yields no alerts. The threat exists entirely within the sequence of relationships connecting those nodes. Solving this requires a topology-native model. Instead of viewing the enterprise as a collection of independent checkpoints, we analyze it as a time-evolving graph. In this graph, a node is an identity, a workload, an AI agent, or a data store. The edge connecting them represents the strict dependency, route, or trust relationship at that exact moment. An advanced persistent threat traverses this network by executing individually plausible, green-lit actions. The attacker composes those actions into an unauthorized sequence of edges, expanding their reachability across the graph. The Predictive Tensor Control Plane, or PTCP, is a control overlay engineered specifically to evaluate the structural safety of these evolving relationships. This diagram illustrates how PTCP tracks that structural behavior. It maps the linear progression of a campaign across 5 tactical stages, documenting how an attacker forces reachability and trust dependencies to drift as they move from initial access to data collection. If a cloud workload suddenly initiates a size volume file transfer, the semantic content might pass data loss prevention checks. But that transfer is structurally unsafe if it bridges a newly compromised collection node directly to an untrusted egress path. Defensive efficacy requires continuously measuring these trust dependencies. We evaluate every access request by asking a broader structural question. Is this specific relationship structurally authorized, expected at this exact moment, and safe for the mission? PTCP is an evidence-gated overlay. It does not replace the deep packet inspection, memory analysis, or domain enforcement provided by native security products. It consumes their verdicts. This reference architecture illustrates the data flow. The observation plane normalizes telemetry from installed infrastructure, requiring exact clock synchronization to bind events to the enterprise topology. This feeds the predictive slow path, where the engine calculates deviations and proposes candidate cuts before attacks advance. Complex graph inference and statistical prediction are computationally expensive. PTCP isolates these calculations entirely off the critical network path, so they never introduce packet-level latency. By separating heavy computation from inline enforcement, the architecture sustains continuous, multi-domain threat modeling without creating an infrastructure bottleneck. Deploying centralized automation carries a critical risk. An unconstrained supercontroller reacting to false positives can rapidly execute enterprise-wide quarantines, causing more operational damage than the adversary. Every proposed action must clear the bounded policy and safety gate. This strips PTCP of supercontroller authority, enforcing strict constraints, rollback sequences, and a critical mission floor. Only approved actions cross into the bounded fast path for immediate execution through native APIs or hooks. The mechanism relies on the smallest safe cut principle. Rather than triggering a disruptive network quarantine, the system severs a single unsafe relationship or freezes a specific AI agent tool, preserving the surrounding healthy dependencies. Finally, an evidence loop permanently records the action. It verifies the physically observed effect against the theoretical expected effect, storing a version state to guarantee perfect operational reversal. This loop preconditions containment. It radically reduces the latency between identifying a threat and actuating a response, while physically guaranteeing business continuity. Evaluating topology native defense requires discarding vanity metrics. Measuring raw alert volume or logging total detected malware signatures provides zero insight into operational survival. The primary quantitative measure of defensive performance is the integral of attacker exposure area. We calculate this by taking the weighted set of reachable assets, RFT, and multiplying it by their critical consequence, WFT. We integrate that product over the time required to achieve safe, verified containment. Because PTCP preconditions a highly specific cut, it actively reduces the RFT variable early in the campaign cycle. This forces the exposure curve down before command and control operations or data collection can succeed. This mathematical model has strict limits. The system cannot reduce risk that is completely unobservable, nor does it claim credit for threats successfully blocked by the native NGSW or WAF baseline. This chart models the Amdahl-style bound on the system. The maximum direct reduction in attacker exposure scales strictly with the percentage of the campaign footprint that is addressable by topological evidence. Operational utility is proven exclusively when this measured reduction in attacker exposure offsets the engineering overhead and any costs incurred by false isolations. PTCP requires a brownfield environment. This matrix details how it integrates, pairing the native deep inspection strengths of platforms like F5 Advanced WAF or Palo Alto's Cortex XSIAM against PTCP's cross-vendor structural reasoning. Integrating this capability requires a mandatory evidence-gated adoption protocol. Engineering teams begin with a 30-day baseline, deploying PTCP strictly to map the current service graph and time-align incoming telemetry. During the 90-day shadow phase, the system consumes live and replayed attack data. It computes predictive candidate cuts and records their counterfactual blast radius, operating entirely without execution authority. Execution authority is introduced in the reversible canary phase. Network engineers authorize low-impact actions, like tagging dynamic groups or isolating test workloads, specifically to drill API resilience, monitor congestion, and test rollback integrity. Broad enforcement is granted only in the scale phase. Signed, cryptographically validated profiles are rolled out on an enclave-by-enclave basis, and only after independent red team replication proves statistical improvement. If the PTCP controller is compromised or isolated by a network failure, the fast paths immediately drop speculative actions. The native vendor endpoints independently fall back to their local, certified safety profiles, ensuring access never silently expands. The objective is to engineer a system where heterogeneous, best-of-breed security products finally operate as a single, mathematically recoverable control plane.